All right, in our next experiment, we're going to be using elemental sulfur, a yellow powdered solid at room temperature. In this form, it actually exists as 8 atoms of sulfur bonded together in a ring. So its chemical formula would be S8. Okay, S8 is the yellow powdered sulfur. I've put some of that in a test tube with some copper metal. Okay, the reddish brown there is copper metal turnings, so just Cu, copper metal. So we're taking sulfur, S8, and we're going to react it with copper, Cu. Now I've got this in a test tube with a rubber dam on top sealed with an elastic band so that it doesn't allow a lot of sulfur vapor into the air as we heat. We're going to heat it with a Bunsen burner as I hold it with these metal tongs. Now, one thing you'll notice as I begin to heat is that the yellow sulfur will have those rings of 8 atoms each break open. It'll turn into a reddish liquid. That's not the chemical reaction we're interested in. So that's just the sulfur turning from the yellow version to a different version of sulfur. But once it's done that reddish liquid will start reacting with the copper metal. Now, at some point, you may see that the reaction produces a bright light. When it does that, the reaction is essentially over. So let's light a burner. And now, when you heat a test tube in a Bunsen burner, always hold the test tube at a 45-degree angle, heat it at the hottest part of the flame, and point it away from you or your neighbors. Okay, so here we go. As I'm heating, the sulfur inside is turning from the yellow sulfur to a liquid. Now right there, I just saw a bit of glowing red. Not sure if you noticed that. There it is there again. So that glowing red, that bright red light, that's a sign that essentially the reaction is finished. Now that happened pretty quickly. I'll stop heating. The copper, there's a little bit of unreacted copper near the top. You can see the reddish brown. But underneath that, you can see the copper is now black. Okay, that black coating on this copper is the product of our chemical reaction. So copper metal reacted with sulfur to produce that black solid material. Remember that the chemical formula for sulfur here is S8. The product is a copper 2+ compound. So that black solid material has copper 2+ in it. In this next experiment, we have sodium phosphate. Sodium phosphate dissolved in water here in the test tube. So that's one of our reactants, and we've got a bottle of blue-colored copper 2 nitrate. Okay, the 2 is missing from that label, but copper 2 nitrate is what's in this bottle here, and it's a nice blue-colored solution. So let's add a few drops, maybe a milliliter or so, of the copper 2 nitrate solution to the sodium phosphate that's in the test tube and observe a reaction. As you can see, there's a precipitate forming. You can think about what that precipitate must be, what type of reaction this is, and what we're seeing in that precipitate. There's another product, which we can't see. That other product is dissolved in the water. Okay, but if you think about what type of reaction this is, you can figure out the 2 products that are produced. The precipitate contains copper 2+. I'll give you that clue. So that precipitate contains the copper 2+ cation. In our next experiment, we have a bottle of bromine water. So this is a solution of bromine. Bromine, of course, is an element on the periodic table. It's one of the halogens, and it's one of the diatomic elements, part of the Hofbrinkel elements. So here it's dissolved in water, but even though it's dissolved, you can probably see there's a little bit of orange vapor above the solution. Bromine at room temperature is normally a liquid. Pure bromine would be a liquid, but it vaporizes easily and turns to gas. It evaporates easily. So here we don't have liquid bromine, that would be too dangerous, but we have a solution of bromine, but some of that bromine is escaping into the air above the bottle. Bromine is often used in hot tubs for disinfecting hot tubs, but it's produced by a chemical reaction when you add certain ingredients to the water, and the bromine then at very low concentrations in the water will kill bacteria and other pathogens. We've also got a bottle of sodium chloride. Sodium chloride is table salt, and it's a saturated solution of table salt. So it's dissolved in water like the bromine, but it's saturated. You might be able to see some of the white solid at the bottom. I've decanted some of the sodium chloride solution into a flask, so we have a colorless solution of sodium chloride in water in that flask. And then we also have our bromine water here in a beaker. Now I can smell the bromine a little bit as it's coming out of the water, so I'm going to do this pretty quickly. I'm going to add the bromine, remember it's orange colored bromine water, I'm going to add that to the sodium chloride. Can you think of what type of reaction this must be? And can you predict what the products would be? So notice as I pour in the orange colored solution, it transforms, and now we have a yellow colored solution. Okay, so the chemical reaction has produced a yellow colored solution. So whatever is produced is dissolved in the water. But as I waft it towards me, I can smell something in there that reminds me of the smell of maybe a swimming pool. I can smell something in there just like you'd smell if you walked into a swimming pool. But right now the products, both of them are aqueous, but one of the products is coming out of the water and I can smell it a little bit as I waft it towards me. So what type of reaction was this? What products were produced? In our next experiment, we're going to take sodium phosphate, okay, so sodium phosphate, and we're going to react that with silver nitrate again. Silver nitrate, again, is a very expensive chemical, hazardous to use. You want to handle it carefully. If you get silver nitrate on your skin, it's going to cause a blackish precipitate to form there. It'll be stained for several days. We've got the silver nitrate already dissolved in some water, and we keep that in a brown bottle. So this is a silver nitrate solution. Over in this test tube, I've got another solution, the sodium phosphate dissolved. So there's sodium phosphate here. You can see it's a colorless solution. And the silver nitrate is also a colorless solution. I'll take some of this into my plastic pipette, and let's add it to the sodium phosphate and observe the reaction. So as I add the silver nitrate with the sodium phosphate, a yellow precipitate is forming. Okay, so that precipitate is rising to the top, so it must be less dense, but it may be over time it'll settle, we'll see. So there's a precipitate formed. That precipitate contains silver, so it's a silver compound. There, of course, is another product being produced. The other product is dissolved in the water and is not visible. Okay, so look at now, you can see the precipitate settling to the bottom of the test tube. It may have had some air or something trapped inside originally. All right, so what type of reaction was this? What classification is it? Can you write a balanced chemical equation for it? All right, in this chemical reaction, we're going to take a look at the reaction of magnesium metal with oxygen from the air. So when we buy magnesium metal, we get it in this kind of package from our supply company. You can see it has a safety symbol on it that says flammable. So this is something you have to keep caution with. All right, for this chemical reaction, we're going to look at the reaction For this next experiment, we're going to look at the reaction between magnesium metal and oxygen in the air. Here I've got a package of magnesium as we get it. You can see it has a safety pictogram on it that indicates it's flammable, so we have to keep it away from sparks and flames. But what we're going to do here today is take a piece of that magnesium metal. It comes as a ribbon like this, coiled up, and we're going to intentionally put it in a burner flame. This is a rather dramatic reaction, and it produces, when you do it in the lab, a very, very bright light, as you'll see, and so safety precautions have to be taken. You don't stare at that light when you do it in the lab, or it can damage your eyes. In the video, it will not hurt you. There's UV light produced in the reaction. So let me light a burner. I'll use some crucible tongs. Take a piece of the magnesium ribbon, and I'm going to start putting it in the flame where it's going to react with the oxygen in the air. The hottest part of the flame, and now it's reacting. Okay, it's producing some white smoke. There's powder in that white smoke. You can see the powder on the end of the tongs that I was using to hold it. And now if I hold that up, you can see that there's a white powdery solid that's been produced. It's also extremely hot, right? So again, we just reacted magnesium metal with oxygen from the air. The product is this white powder. Okay? You can think about what that must be, what type of reaction this was, and then identify that white powder product. So in our next experiment, let's look at the reaction again between silver nitrate. We've seen this in a couple of other reactions, but this time we're going to react it with copper metal. Copper, of course, is just the element copper. We've got it coiled up here in a wire. I've got over here a test tube with the solution of silver nitrate. So silver nitrate dissolved in water. And let's add the copper wire to the solution. Okay, now you may be able to see the unreacted copper is above the solution. You can see it's reddish brown color. And where it contacted the silver nitrate solution, it's immediately turned gray. So there's some kind of precipitate occurring on the surface of the copper wire. We're going to let this sit for a while, and we'll come back to it and see how it looks after, well, maybe 30 minutes or so of reacting. All right, a few minutes later, now I've got a piece of white paper as a background. You can clearly see the solution now has a definite blue tinge to it. So something in the solution is causing it to have a blue color. And that precipitate on the surface of the copper wire is definitely a light gray, silvery colored crystal structure. You can see perhaps if you look very closely, some fine crystal shape to it. So it's some kind of solid gray material. So can you classify the reaction occurring and think about the two products that are being created here? All right, in this next experiment, we have sodium hydroxide, and we're going to react the sodium hydroxide solution with iron 3 nitrate. So this is iron 3 nitrate solution that we're going to be using. The iron 3 nitrate solution is a yellowish solution, okay? And the sodium hydroxide is colorless, like water. I've diluted the sodium hydroxide a little bit with some distilled water, and we have that here in a test tube. Let's add some of the iron nitrate, iron 3 nitrate solution to the sodium hydroxide solution and see what we get as a product. Okay, you can think about what type of reaction this should be and think about what the products would be if we react these together. Okay, so as I add the iron 3 nitrate, you can see there's some kind of rusty colored precipitate that forms That rusty colored precipitate is rusty colored because it contains the iron 3 plus cation. All right, so there's iron 3 nitrate reacting with sodium hydroxide. One of the products is that rusty red precipitate, which contains the iron 3 cation. Can you classify the reaction and think about the products that will be forming here? One of the two products is dissolved in the water, so we won't see it, but this reddish brown product, this precipitate, is a solid, and we can see it come out of the solution. If we give it time, it's going to slowly settle to the bottom of the test tube. For our next experiment, I've got a bottle here of cyclohexane. Cyclohexane, you can look up the chemical formula for that. All right, so it's an organic compound, meaning it's got carbon and hydrogen in its formula. Like many organic compounds, it's highly flammable. So in our storeroom, we have to keep these things in a special cabinet, a metal cabinet for flammable materials, so they stay away from open flames. Now I've got here a petri dish with a little watch glass on top. I'm going to take a bit of the cyclohexane with a plastic pipette. I'll put some of the cyclohexane, just maybe a milliliter or so, on the watch glass. So there's about a milliliter. I'll put the lid back on, and I'm going to put that bottle off to the side. All right. Now I'm going to turn the lights off, and we're going to try to ignite the cyclohexane with a burning wooden split. All right, so the lights are off. Again, there's just about a milliliter of the cyclohexane in the watch glass. Now, one of the dangers of flammable liquids, let me see if I can get that to burn. There we go. One of the dangers of a flammable liquid is that not only is the liquid flammable, but its vapor is flammable. So you definitely want to keep the bottle of chemical far away and have its lid completely covered if there's an open flame nearby. Generally, you should handle these things only in a fume hood, which would take away the flammable vapors and prevent the dangers involved. So think about what's happening here. Think about what type of reaction this is and what the products must be. You may need to look up the chemical formula for cyclohexane in order to write your balanced equation. All right, in this next experiment, we've got a bottle of potassium metal. Potassium, of course, is an alkali metal on the periodic table. It's found in the first column on the left side of the periodic table. It's a highly reactive alkali metal, so it's kind of dangerous to have around. I've got a petri dish here, and I'm going to put some distilled water in the petri dish. Let me just fill the dish with water, and we're going to look at the reaction that happens between potassium metal and water. Very famous reaction. Now I've got some litmus paper, red litmus paper. We've used this before. Red litmus paper, if it's in the presence of an acid, will stay red. If it's in the presence of a base, it'll turn blue. Okay? If it's in something neutral, it would also stay red. So if I just put the litmus paper into my petri dish of water, nothing really happens. It just gets wet. So that tells me there's no base present in the water. Okay? Now, take our bottle of potassium metal, and the potassium is stored under oil. Okay, so as I take it out, you're going to see that it is dripping with some kind of liquid. That liquid is oil. Okay, it prevents the potassium from contacting the air and also from contacting anything else. So I'll take it out of the bottle, a rather big piece of it, and you can see some oil dripping off. Let me put the lid back on the bottle. Okay, I'm going to use a scalpel. Okay, take a look at the surface of the potassium. You can see it doesn't look very attractive. It's dark gray. Okay, it's basically corroded. It's a pretty soft metal. I can impale it with my tweezers. So soft I can cut it with a knife. So I've just cut it, and where I've cut it, you should be able to see that it's much shinier, which of course is a property of metal elements. So I'm going to take the large piece of potassium and I'll put it back in its bottle for safety. Put the lid back on. All right, so now we have a small piece of potassium metal. You can see the paper towel has soaked up some of the oil from the potassium. Now, as I put it into the water, let's see what reaction takes place between potassium metal and H2O, water. Okay, so you can see a lot of smoke is being produced. That smoke is because there's a highly exothermic reaction and the heat is causing the oil to burn. But you saw a flame as well, a purple flame. That purple flame is the characteristic flame test color for potassium metal. But why was there a flame? The reason is that there was a flammable gas being produced as it reacted. The gas being produced that's flammable was hydrogen gas. And the heat from the reaction of the potassium and the water caused that hydrogen gas product to ignite. And as it burned briefly, you saw the purple color, the lilac color, the characteristic test for potassium. Now, I've got my litmus paper here. What happens if we take our litmus paper, the pink litmus paper, and put it in this watery solution now? Does that tell me anything interesting? As I put the paper in there, swirl it around, okay, you may be able to tell that the paper has turned blue. Okay, so the paper has turned blue, is meaning something in that water is now basic. Okay, so one of the products of the reaction was a flammable gas. The other product is dissolved in the water, and it's causing it to become basic. So can you classify the reaction between potassium metal and water and think about what these two products must be as you write your balanced equation? All right, for this next reaction, we've got a bottle here of ammonium carbonate. Okay, ammonium carbonate. As soon as I opened that bottle, I could smell something coming out of it. I've put a little bit of that powdered ammonium carbonate, it's a white solid, I've put it into a dry test tube here, and we're gonna light a Bunsen burner and start heating it. Now, I've also got with me some cobalt chloride test paper. Cobalt chloride test paper is a blue paper, sort of like litmus paper, but not quite the same. It's just filter paper with this cobalt chloride dissolved into it, and then it lets it dry. So we've got cobalt chloride paper. It starts off blue, but it's dry. Now let me take some distilled water, and I'll put some distilled water on a watch glass, and take a look at what happens when cobalt chloride test paper gets wet. So put that cobalt chloride paper in the water, and you can see that it turns pink. So when cobalt chloride comes in contact with water, it turns pink. Now we've got something a bit more familiar also here. We have a vial of red litmus paper, okay? Litmus paper, of course, is used to test for acids and bases. Red litmus paper, when you put it into a base, turns blue. So if there's a base present, the red litmus paper turns blue. All right, so we've reset. Let me light the Bunsen burner here. And we'll place that burner under the test tube with the ammonium carbonate. Okay, now can you make some observations just as you see the ammonium carbonate being heated? I'm going to take my litmus paper here. I've got my red litmus paper. I'm going to get it wet. Just dip it in that distilled water we saw earlier. I'm going to put the red litmus paper in the mouth of the test tube. Okay, so you can see it dramatically turned blue. So there's some kind of base being produced as we heat. Let me also take the blue cobalt chloride paper, and I'll put that, touching it to the side because there's something condensing on the side of the test tube. As I touch it, I think you can see there, it is changing color. It's turning sort of a pinkish brown color. So that tells you what another product is. So there's two products that we know. One of them is a base. Now, do you notice what's happening at the bottom of the test tube where that solid was? So the solid material, the ammonium carbonate, appears to be disappearing. I've got a wooden splint on fire here. Let's see what happens when we put that in the mouth of the test tube. Okay, so the flame was extinguished. Okay, now there's three products in this reaction, and all three of them are gases. So if you look at the bottom of the tube, it's now empty. The solid material has completely turned to gas, and there's three gaseous products here. One of them we proved the identity of with our blue cobalt chloride paper. We know that one of the products is some kind of base. It turned pink litmus paper blue. And a third product caused the burning wooden splint to be extinguished. So can you think about what those three gaseous products would be? You might want to start by writing the chemical formula for ammonium carbonate and think about what kind of reaction this was. So the solid completely turned into gaseous products. All right, for our next reaction, we're going to take sodium iodide, in our next experiment, we'll take a solution that contains potassium iodide. Potassium iodide is a white salt, but we've dissolved it in water here, and I've poured some of that solution with the potassium iodide in this test tube. We've also got lead 2 nitrate. The lead nitrate is also a white solid salt at room temperature, but we have it also dissolved in water. Now, lead compounds are hazardous. You don't want to ingest that. You don't want to pour them down the drain. They're bad for the environment also. So we'll have to dispose of this afterwards in a safe way. So I've got my lead nitrate in a plastic pipette. Let's add it to the potassium iodide and observe the reaction. All right, so as I added the lead nitrate, you can see a rather beautiful yellow precipitate has formed. That yellow solid material is slowly sinking to the bottom of the test tube. It contains lead, so that yellow solid is a lead compound. There's a second product produced, but it's soluble in the water, and it's not colored, so you can't really see it. But there is a second product also of that reaction, and it's aqueous, dissolved in the water. All right, can you classify that reaction and write a balanced equation? Our next experiment is not going to be the most dramatic chemical reaction. We have a candle here. The candle's got paraffin wax in it. Now, in reality, paraffin wax is a whole mixture of molecules that are made of carbon and hydrogen. For simplicity's sake, we'll assume that this particular candle wax is made of just one of those compounds. We can call it C30H62. That would be its molecular formula, C30H62. In fact, there'd be a whole slew of molecules in there with slightly different formulas, but we'll assume it's made of that pure compound. Now, in the video, I'm going to be using something called cobalt chloride test paper. Basically, this is just a piece of filter paper that was dipped into concentrated cobalt chloride solution and then allowed to dry. So it's a blue piece of paper. I've put some distilled water onto a watch glass here and show you what happens when cobalt chloride test paper gets wet. So we have this blue paper, put it in the water, and it turns pink. So the blue cobalt chloride paper turns pink when it gets wet. And that's its function as a test for the presence of water. You can use it to test for humidity as well. So I'm going to take a match and light our candle. So as the candle burns, the paraffin, the C30H62 compound, is melting, and then as it melts, it vaporizes and rises, and that creates the flame that you see there. Now I've got here a glass jar, just an empty glass jar with a wide mouth to it. I'm going to hold that over the candle. I want to collect some of the gases that are being produced as it burns. So this compound C30H62 is burning, and it's producing some kind of gaseous products. Now, as I hold the jar over the flame with the mouth very close to the flame, I'm not sure if you can tell in the video, but it sure looks to me up close that the inside of that jar is getting cloudy. It looks like it's fogging up somehow. All right, so I'm going to collect it for a little bit longer. Now I'm going to put the jar, so there's something in there that's causing the glass to get cloudy. Now look what happens if I put this jar, which is now full of the gases from the burning candle. What happens if I put the jar just right over the candle? I'm going to lower it slightly. Take a look at what happens. Okay, so you can see as soon as I put it down, the flame from the candle was instantly snuffed out. So one of the products of that burning compound caused the flame to be instantly extinguished when we collected the gas and then used it to put it over the flame. Now let me take a fresh piece of this blue cobalt chloride paper. I'm going to put that inside the jar, and I'm going to rub it around because I said there was something in there that looked kind of foggy. So as I rub it around, I'm wiping away that fogginess, and look what happens to my cobalt chloride paper. It turns from blue to pink. So that tells you that coming out of the burning candle, there were two things. One caused the cobalt chloride paper to turn from blue to pink. The other caused the flame to be extinguished as soon as I put the jar over top. All right, so two products from burning the candle. In this next experiment, we're taking sulfuric acid with a concentration, if you're interested, of 3 moles per liter. That makes it relatively concentrated, but it's still dissolved in water, so this is mostly water, but it contains sulfuric acid. We've also got a metal, okay, zinc metal. It's actually referred to as mossy zinc in this case. Molten zinc, melted zinc, was poured into water. As it cools quickly, it forms the solid zinc, and it's referred to as mossy zinc. But you can just think of it as zinc metal. So we have the element zinc, the compound sulfuric acid, and let's put the zinc into the acid and observe if there's a chemical reaction. All right, so as you take a look, you can see there's not a huge amount going on. There's a little bit of evidence of some bubbling occurring. I'm going to add a bit of a catalyst. A catalyst will speed up the reaction a little bit. The catalyst I'm going to add is a copper sulfate solution, but it really just speeds up the reaction if there is one. So let's add the copper sulfate and then see what happens. So you can see now the reaction between the zinc and the sulfuric acid is much more vigorous. It's producing some kind of gas. So why don't we collect the gas and we'll see what that gas is. All right, so I've placed an empty test tube above the test tube with the zinc and sulfuric acid reacting. It's been sitting there for about 30 seconds. I'm not sure if we're going to get enough gas produced to test it successfully, but let's give it a try. So I'll put that down. See, I think I know what gas that is, so I'm using a very characteristic test. I've got a wooden splint on fire. Let's see what happens when we put that into the gas. Yeah, I think you heard that. There was a little bit of a whooping sound as the gas inside the test tube burned in the flame. So that gives you a clue as to what gas is being produced as the zinc reacts with the sulfuric acid. What type of reaction is occurring? What must the two products be of the reaction? Okay, keep in mind that we added some copper sulfate to speed up the reaction. It was a catalyst, but you shouldn't include that in the balanced equation between zinc and sulfuric acid. All right, for our next experiment, we're going to look at the reaction between two compounds. Sodium chromate, you can see there is a rather nasty chemical. We're going to have to dispose of this afterwards in an environmentally friendly way, and we take appropriate safety precautions when using it. And it's a yellow solid, by the way, a yellow salt. I've got some of it dissolved here in some distilled water in a test tube. So this yellow solution is a sodium chromate solution. We've also got some very expensive silver nitrate. Okay, silver nitrate, because it contains silver, is a very expensive chemical to obtain. We've got a bottle of the silver nitrate already dissolved in water here. Okay, it's a silver nitrate solution. We keep it in a dark bottle because silver solutions are sensitive to light. The light will react with the silver nitrate and cause it to become silver metal again. So I've got some of the silver nitrate in my eyedropper, my little plastic pipette. Let's put some of the silver nitrate in with the sodium chromate and observe the reaction that occurs. Okay, so you can see as we add the colorless silver nitrate solution with the yellow sodium chromate solution, a reddish solid precipitate is being produced. Okay, that solid precipitate has silver in it. I'll give you a clue. So this reddish brown precipitate, solid material which is now settling to the bottom, it's a silver compound. So you can think about what type of reaction this is, and you can predict what product that reddish brown solid precipitate is. Of course, there's another product produced. The other product is dissolved in the water, so it's not visible. All right, so I've got here a test tube full of gas, but not just air. I've actually filled the test tube with hydrogen gas. Hydrogen, of course, is an element. It's one of the diatomic elements, the Hofbrinkel elements. You've seen me, if you've watched some of the earlier videos, you've seen me do something like this already, but I want you to focus now on what's actually happening in this particular reaction. If this test tube is full of hydrogen gas, I'm going to lift it off the bench so it'll be exposed to air. Now, air is mostly nitrogen, but air does contain oxygen as well. So the hydrogen gas that's in the test tube will react with the oxygen gas from the air as I put a burning flame to it. Let's take a look. All right, so you heard and maybe saw the flame there. That exploding sound is characteristic of evidence for hydrogen gas. If you put a burning wooden splint into hydrogen gas, you get that characteristic popping sound, which is the result of the reaction between hydrogen and oxygen gas from the air. Okay, so what type of reaction must that be? What must the product be? Okay, think about that. All right, in this next experiment, we're going to take a solution that contains copper 2 chloride. So that's what you see here, this bluish green colored solution. So copper 2 chloride dissolved in water. And we're going to add to that a piece of aluminum metal. Okay, so the aluminum is going to react with the copper 2 chloride. Let's take a look at what happens here. the aluminum into the solution. And you should be able to see immediately some evidence of chemical change. All right, so we're revisiting the test tube. It's been, about 10 to 15 minutes of reacting. The original blue color of the solution is almost entirely gone. There's a very faint green color, and if we let it go for a bit longer, the solution will eventually be colorless. You can now clearly see that reddish-brown precipitate coating the aluminum wire, and if we took it out, the aluminum wire would be much thinner than it used to be. So the aluminum has been reacting with the copper chloride and producing this precipitate on the surface of the wire. There is another product to that reaction. It's a substance which is dissolved in the water, so you can't really see it. And once again, the aluminum is doing another reaction, which we're not really interested in. It's also reacting with the water, and we tested earlier and showed that that was probably hydrogen gas being produced.